In this lecture we will discuss mechanism of E1 elimination. Then we will discuss evidences for E1 mechanism. We will also see the competition with SN1 reactions. Then we will discuss regioselectivity of E1 reactions. At the end we will discuss factors affecting E1 reactions. To understand E1 reaction mechanism, consider this tertiary butyl bromide substrate. Upon treatment with weak base ethanol, what is formed is this substitution product, wherein bromide is replaced by ethoxy group and an elimination product 2-methyl-1-propene. This substitution product forms almost 81% of the product mixture, and this elimination product forms 19% of the product mixture. For now remember, this is formed by SN1 and this by E1. Because the rate of appearance of both products follows first-order rate law. Rate equals K times tertiary butyl substrate. It is easy to recognize that the substitution product is formed by an SN1 mechanism, because the starting alkyl bromide is tertiary. Because the elimination reaction follows the same rate law, its rate-determining step, like that of SN1 reaction, must also involve only a molecule of tertiary butyl bromide. Therefore, the elimination reaction is described as unimolecular elimination or E1. To understand the formation of both SN1 and E1 products, consider the substrate tertiary butyl bromide. The first step for both substitution and elimination is the formation of the carbocation formed by removal of bromide anion leaving group. This is the rate-determining step for both substitution and elimination. In case of elimination, the weak base abstracts the beta hydrogen to form an alkene. Of course, as shown earlier, it makes 19% of product mixture. This is E1, because rate-determining step has only one molecule, which is substrate. The other possibility is that weak base ethanol acts as nucleophile and attacks the positively charged carbocation to form this positively charged substitution product, which is deprotonated by other ethanol molecule. We get this substitution product which makes 81% of the mixture. This is off course by SN1. The E1 reaction follows the same rate law as the SN1 reaction because both mechanisms have the same rate-determining step, the formation of the carbocation, as shown in energy profile diagram. In the second step of the mechanism, the ethanol can react with the carbocation as a nucleophile to give the SN1 product or as a base to give the E1 product. Under these particular conditions, the transition state, for the second step, leading to substitution is slightly lower in energy than the transition state leading to elimination. So the substitution product is the major one. If an elimination is possible, if there is a beta hydrogen, then some elimination product always accompanies the substitution product in SN1 reactions. Because the amount of elimination is difficult to control, this detracts from the usefulness of these reactions to prepare other compounds. In addition, carbocation rearrangements may lead to rearranged elimination products as well as rearranged substitution products. Therefore, these unimolecular SN1 and E1 reactions are not a good choice for synthesis of other compounds but are usually used to study the structure and reactivity of the carbocations. Some of the evidence for the E1 mechanism is as follows: the reaction exhibits first-order kinetics, in substrate, as expected. Of course, the solvent is not expected to appear in the rate equation, even if it were involved in the rate-determining step. For example, tertiary butyl bromide on treatment with ethanol gives this elimination product. We can check the involvement of solvent in rate-determining step by adding a small amount of the conjugate base of the solvent. It is generally found that such an addition does not increase the rate of the reaction. If this more powerful base does not enter into the rate-determining step, it is unlikely that the solvent does. Such observations confirm E1 mechanism. If the reaction is performed on two molecules that differ only in the leaving group, the rates should obviously be different, but ratio of elimination to substitution products should be same. Consider these two reactants which differ only in the leaving group. When these compounds were solvolized at 65 degrees Celsius in 80% aqueous ethanol, product distribution was obtained like this. We can clearly see that the rates were greatly different, as expected with such different leaving groups. However, the product ratios were the same, within 1%. If this had taken place by a second-order mechanism, the product ratios would have been different because nucleophile base would have different preferences for the beta hydrogen with respect to neutral chlorine and positive SME2 group. The third evidence for E1 mechanism is that the relative stereochemistry of the leaving group and the hydrogen is not important in the E1 elimination. We will understand it by subjecting methyl chloride to E1 elimination conditions. The two different types of beta hydrogens are shown in cyan and red color. Since E1 has carbocation intermediate, therefore any of these cyan or red hydrogens can be abstracted by base to form the alkene products. However, as we have seen in the lecture on E2 elimination that E2 reactions are stereospecific, the same substrate under E2 conditions will give this product only, because only the cyan hydrogen trans to chlorine will be abstracted by base to form the double bond. The first-order reaction conditions will also give good percentage of substitution products also. Thus E1 conditions give mixture of alkene products, since the steric nature of the beta hydrogen is no longer a factor, and the more stable alkene, Zaitsev product is predominantly formed. The fourth evidence is that, in the E1 mechanism, carbocations are intermediates. Therefore, we should expect rearrangements with suitable substrates. These have been often found in elimination reactions that are performed under E1 conditions. Consider this particular substrate subjected to E1 conditions. The first step will be of course the removal of bromide leaving group to form the carbocation. This is secondary carbocation. This carbocation has tertiary carbon adjacent to it. Therefore 1,2-methyl shift generates a secondary benzylic carbocation, which is more stable than simple secondary carbocation. Now both the carbocations can lose a beta hydrogen to form alkene products. This secondary carbocation loses a beta proton to form this alkene, whereas this benzylic carbocation loses a beta proton to form this alkene. This alkene is less substituted of the two, and we call it normal product because it is formed from the carbocation directly generated from substrate. This alkene is more substituted and is called rearranged product because it is formed from the rearranged carbocation. Given the stability of product and carbocation from which it is formed, this less substituted alkene is minor and this more substituted alkene is major product. In case of regioselectivity, Zaitsev rule is generally followed in E1 reactions. Thus, when two elimination products can be formed, the major product is always the one which is more substituted. As an example, consider this alkyl bromide subjected to E1 conditions. There are two types of beta hydrogens with respect to carbon-bearing bromine leaving group. Thus, two alkene products are possible. This more substituted alkene will be major and this less substituted will be minor. We call this Zaitsev and this Hofmann. Moreover, in the E1 reaction, trans double bonds are generally formed more readily than are cis-substituted double bonds. This can be understood if we draw the activated complex for the formation of cis and trans alkene. Consider this activated complex for cis-alkene formation. The carbon-bearing positive charge is on front with empty p orbital, it is attached to methyl and hydrogen. The back carbon is shown in cyan blue circle, which is attached to methyl and two hydrogens. The removal of one of the beta protons leads to cis-alkene formation. In the activated complex, you can see the two methyls close to each other causing steric strain and making the activated complex higher in energy and hence less stable. In the activated complex for trans-alkene formation, you can see the two methyls are away from each other and hence no steric strain as seen in activated complex for cis-alkene. Thus this activated complex is lower in energy and hence trans-alkene is formed more readily. If beta-carbon has only one hydrogen, the E1 elimination gives both E and Z alkene as products, with E alkene being the major product. On the contrary, E2 elimination with such substrates gives only one isomer because E2 elimination is anti. Consider this substrate. If this is subjected to E1 conditions, we get both E and Z alkene products, with E being the major product. Likewise, consider this substrate, wherein we change the orientation of ethyl and hydrogen on beta-carbon, is subjected to E1 conditions. We get the same product mixture with E alkene being major product. Compare this with E2 reactions. If this substrate is subjected to E2 conditions, we get only E alkene as product. Because E2 is stereospecific, the leaving group chlorine and beta hydrogen are perfectly in trans arrangement in this substrate and are eliminated without changing the orientation of any other group. The ethyl groups are trans in product as they are in reactant. Same is the case with methyl groups, trans in substrate and in product as well. The other substrate upon subjecting to E2 conditions, gives only Z alkene as product. This is because, in the substrate, leaving group chlorine and beta hydrogen are cis and elimination cannot take place in this conformation. For E2 elimination, the leaving group and hydrogen must be trans to each other, and in that particular conformation, the ethyl groups and methyl groups are cis to each other to make Z alkene as the only product. Thus we understood that, for E1, stereochemistry of beta hydrogen does not matter. Thus, E1 is non-stereospecific, and E2 is stereospecific. Now we will discuss factors affecting E1 reactions. First is substrate structure. Since E1 reaction takes place by the formation of carbocation as reaction intermediate, thus the rate of the E1 reaction depends on the stability of the carbocation. Since inductive effect, hyperconjugation and conjugative effect stabilize carbocation, any structure which forms stable carbocation will be reactive. Steric strain around the leaving group also favors the formation of carbocation. Thus we can say that reactivity of alkyl halides parallels the relative stability of carbocations. This means among simple alkyl halides, tertiary is more reactive than secondary, which is more reactive than primary. Therefore, alkyl and aryl substitution on beta-carbon with respect to the leaving group increases the rate of E1 reactions. The second factor is strength and concentration of base. The strength and concentration of base have nothing to do with the rate of E1 reactions. Even the solvent molecule serves the purpose of base for E1 reactions. The third factor is nature of the leaving group. Reactivity of the substrate depends mainly on the nature of the leaving group. The best leaving group are those which are least basic and more polarizable. Thus the decreasing order of the leaving group reactivity is iodide more than bromide, which is more than chloride, which is more than fluoride. The fourth factor is nature of the solvent. Because of the ionic carbocation intermediates, the rate of E1 reaction increases with increasing polarity of the solvent.